Welcome to the third and final live session of the course Matrix Solvers. Because we are almost at the end of the syllabus and the exam will be up in next couple of days, I thought it will be good if we can have a live session once, and if you have some specific queries, I like to also address them, and also like to give you a complete view of the syllabus, from which you probably will get some pointers how to get your last minute preparation done for the exam. So, in case if you have some specific queries, you can send me. I got a couple of queries from just a second, from I got couple of queries, I forgot his name, from professor. Just 1 minute, let me tell his name. So, just hold a minute, I will tell his name who will send the queries from the Google form, and I will also look into the Google form once more. And see if there is any more query. So, this is Professor Guru Vishwanathan, who was, just write it down, who was who probably cannot be present today, but sent his queries. So, the first one is regarding the assignment 8. There is a question where the answer was wrong, and we must apologize that for some assignments the answers are not picked up correctly, as there is a team working for the entire assignment. In certain cases we had some coordination issues. However, we have noted down all the doubts sent by the students, and in right cases we have identified which answers should be, like in many of the cases there is one extra answer which is probably also right. We are giving marks for both the answers, and this is being taken care of. So, do not worry for that. So, assignments that have multiple answers, for if one answer is correct, you will get the full marks. The next one is that how to find functional form of infinite solution using matrix operation. So, this is we will probably like to quickly discuss this. So, in case Professor Guru Vishwanathan's first question is that how to find functional form of infinite solution using matrix operation. So, if I have a matrix Ax is equal to B and A is singular, however, B lies in the column space of A, then this matrix has infinite solutions. So, we split this solution as A x n plus x p is equal to vector 0 plus vector b. That is, A x n is equal to 0 is one equation, and A x p is equal to b is another equation. So, this is the particular solution, and this is the null space. So, in less number of words, we can say that in case Ax is equal to b has infinite solution, the solution x is basically null space of A plus a particular solution x p which satisfies x is equal to b. So, if one solution x p I can find out which satisfies x is equal to b, I can add this with any of the null space vector and I will get a solution. Now, we can probably check how we can get the null space and the particular solution, which I have done it in quite detail. You can find it in, say, lecture 16. you can find it in lecture 16, that you have to transform the same. In case we are solving this equation A x is equal to b, this is your A matrix, this is the x and this is the b vector, and this has multiple infinite solution because this is a singular matrix, the matrix A is a singular matrix. So, we first solve the null space equation. While solving the null space equation, you start with A x is equal to 0 and get a reduced row echelon form, of A matrix. Now, once you got the reduced row echelon form of A matrix, you have to identify the pivoted columns and the free columns. The vectors associated with the free columns, like the second column is a non-pivoted column. So, the second element of vector x n is a free vector. Similarly, fourth is a non-pivoted column. So, this is y is also a free element. So, these are the free variables, and you can probably follow the steps I have worked out in lecture 16 and see that how you can get the different null space solutions. So, these are the two basis vectors of null space, and therefore, any combination of them will be the null space vector. And then we go to solution of the particular integral or x p, the particular solution x p, and while solving x p is equal to b, we again get a reduced row echelon form of A, and the B matrix vector, when we are doing this earlier, we are doing x is equal to 0 and getting reduced to echelon form. So, the 0 vector does not change, but when we are operating over B vector, due to all row operations, B vector changes to C. And now, we have observed that the infinite solutions are due to the free variables. So, what do we do here? We just take off the free variables and we assume all the free variables are 0, because they are already considered in the infinite solution or in null space vector. So, we remove the free variable columns and solve the equation 2 by 2 equation system here, or whatever will be the equation system. So, you remove the free variable and it will be a non-singular matrix and solve the equation system and get the particular solution, and then you add the particular solution with the null space solution with, and this v and y may have infinite value. So, there can be infinite vectors, and this is typically is the functional form of A x is equal to b when it has infinite solutions. So, this is the particular solution, and any solution will be a linear combination of these two vectors with this particular solution. Okay. So, this answers the question, when there are infinite solutions, how we can get the functional form of the solution. The functional form of the solution will be again nothing but x there is some issue here. But probably have to exit and restart it. So, and you can see that there are more examples, actually you can browse through it. So, if I have an equation system A x is equal to b with A singular, b belongs to column space of A, so that x has infinite values, the functional form x is equal to some vector in the null space of A plus a particular solution x p with A x p is equal to b. So, if any x p satisfies x p is equal to b, I add null space of A with this will be the functional form. The next question is how to find the nearest approximation for no solution case. So, no solution case of x is equal to b can again happen if A is singular, but B belongs to column space of A. B does not belong to column space of A. If B belongs to column space of A, there are infinite solution. If B does not belongs to column space of A, there is no solution. For having any solution, the right hand side vector must be a member of the column vector of the column space of the main matrix. So, by least if A has the solution can the nearest solution can only be obtained if A has independent columns. If A does not have independent column, then this is more critical. We have not discussed it, but you have to actually remove the dependent columns from the A matrix and trim down the equations. But we can consider the case where A has independent columns, and through least square or through projection, we get the equation A transpose A x tilde is equal to A transpose B, and this x tilde is best estimate of x. So, the nearest solution is obtained as A transpose A tilde, A transpose A x tilde is equal to A transpose B. As A has independent columns, A transpose A is a full rank matrix, is a square matrix and will be a full rank matrix. Therefore, A transpose B will always be a member of column space of A transpose A. So, this will always have a solution, and this x tilde is called the nearest solution or the best estimate. And this is again discussed in quite detail in lecture 23. So, you can I have given a few examples on that. So, you can look into lecture 23 and find it. Well, is there any other question? I think somebody else has also sent a question. For solving, okay, for solving. So, this question is from G. Vikram, Vicky. I saw your postings and questions earlier. So, let me look into the question. For solving x is equal to b, when to use direct solvers and iterative solvers, and there is another question. What are the advantages and disadvantages? Okay, it's a very good question. Actually, it's of good practical use if we can have an insight on that. So, when should we use iterative solvers and when should we use direct solvers? Direct solvers are in a way very good. We do not need to go for iterations. In one step we will get all the solutions. But we have seen that direct solvers, if I can discuss for a general matrix, not for tridiagonal matrix, there is a nice algorithm TDMA, but for general matrix, if I consider Gauss elimination or LU decomposition, or if I consider Kramer's rule, these are few methods of solving finding direct solution. The number of operations is of the order of n cube if I have an n into n matrix. So, if I have a small A matrix, say I have a 4 by 4 matrix, number of operation is 4 cube, 64 into 4, 256, which is not very high, and in a gigaflop machine or even in a megaflops machine, you can get it in few seconds, even less than a second. So, if the matrix size is small, it is always worthy to go for direct solvers, and in many cases we deal with smaller matrices. There are a number of cases. We think of a kinematics problem with finite number of 8-10 linkages. You are dealing with 10 by 10 matrix or maybe 30 by 30 matrix if you consider 3 degrees of freedom. So, it is a small matrix, you can get the solutions first, the number is n cube. If it is a large matrix, say you are doing a finite element calculation of 50,000 mesh points. So, then the number of operations will be 50,000 cube, which is a large number. Therefore, direct solver will take very large time, as well as in each operation it will do some numerical error. We have seen about round of errors, so in each operation there will be round of error. So, this round of errors will be piled off, and finally, we will see a lot of error in the results also. The results we have discussed about Gram-Schmidt and modified Gram-Schmidt method, that numerical errors can actually kill the solution. So, we will get many we can get a wrong solution also. In these cases where we have large matrix, it is probably better to go for iterative solvers, because if I see say GMRES, one of the best iterative solvers, the number of iterations is of the order of n. So, if I have 50,000 matrix, it cannot be more than 50,000 iterations. In each iteration, we are solving a smaller matrix. So, the number of operation is never going to be of the order of n cube. In GMRES, we solve a smaller minimization residue minimization equation, which is even if we think of a matrix equation which is not of that large matrix, of a smaller matrix. Also, in these methods, in iterative solvers, we use the fact that we are most of the time dealing with sparse matrices. So, we do not do operation in each row, in each element of the row, we only do operations in the non-zero elements of the row. Therefore, the number of operations are also reduced, and the number of steps to converge is small. So, in a whole, the total number of operations is small. If the matrix is large, the total number of operation in an iterative method is smaller than the direct solvers. And also, we are doing round of error in each iteration, but after each iteration we are using the last iteration value as a guess value and starting the new calculation. So, the round of error do not pile up beyond one particular iteration, because we are only updating guess value, and any error in guess value is fine, I am going for a better guess in next time. So, the overall round of error is less. So, in a whole, if I have small matrix, it is sometimes very advantageous to go for direct solvers, because we get faster solution, the complexities are less. But if we have large matrix, it is almost a law that you should go for an iterative solver, except for very few special cases when you have certain direct solvers for that special type of matrices, like TDMA. It uses a direct solver, but uses a recursive relation, and the number of iterations are very less. It solves everything in order of n operations. So, even if the matrix is very high, TDMA will give you a first solution, but the matrix has to be tridiagonal. So, not every time we will get a nice matrix like a tridiagonal matrix, we cannot use TDMA for all the cases. And in some time we can have, even for a pentadiagonal or septadiagonal matrix, we can take some advantage of TDMA and use an iterative solver based on that, which you use an alternating direction implicit method or ADI method. ADI is essentially an iterative solver, but it uses TDMA for the small matrix equation. So, it is a very fast solver in a sense. So, the rule of thumb is that large matrix, this is again a question, what is large and what is small. This depends on which type of computer you are using, what is the processing power of the computer, what is the RAM size of the computer, etc. But in a sense, a 50,000 matrix can be considered as a large matrix, a 20 by 20 matrix can be considered as a small matrix. So, for a small matrix, it is advisable to use direct solvers. For large matrix, it is advisable to use iterative solvers. This probably is valid for most of the cases, except the case you have a nice structured solver like tridiagonal matrix. Okay, we have any other question? Okay. So, as I do in maybe there will be more questions, but as of now there is no more question. What I will do is that I will what I have done in other live sessions, I will try to give you a brief overview of the topics covered after the last live session. So, precisely confine myself to the discussion of Krylov subspace based solvers and others, and will probably discuss a few pointers regarding the exam also. So, we started with Krylov subspace based solvers with a view that the iterative solvers based on the projection methods can be more efficiently implemented. General projection method like minimum residual, steepest descent showed lot of potential. In a sense, steepest descent can be applied for any symmetric matrix, it may not be irreducibly diagonally dominant matrix. Minimum residual matrix can be applied for non-symmetric matrix also, again diagonal dominance is not strictly required, and if we go to the residue norm matrix, it can be applied for any matrix, but we have seen that the number of iterations are very high even compared to something like a basic iterative method with successive over relaxation SOR etc. So, we notice that these methods are using one dimensional projection. So, the idea is that how projection process can be improved, because so this is the initial vector and this is the final, this is the initial guess, it is a vector. So, this is a vector in 3D space and this is the final vector. They are not related through any single vector. So, if I start from one vector and reach it, you have to go through a 3-dimensional space. In large matrix, you have to go through a multi-dimensional space. So, we looked into multi-dimensional projection system and we considered the idea of Krylov subspace, because it follows very closely the steps of steepest descent. If we consider n number of steps of steepest descent, this is probably a Krylov subspace of grade n. So, you choose Krylov subspace method, and then we have seen that in Krylov subspace something like though the initial basis vectors are r, a r, a square r up to the point that it follow Carey-Hamilton principle and we do not produce any dependent vector, we get a large number of independent vectors. However, if we can orthonormalize them using modified Gram-Schmidt, we can get nice basis vectors of Krylov subspace, and we tried to get that using Arnoldi's method, Arnoldi modified Gram-Schmidt method, and then we use this for solving linear equations using the idea that in an orthogonal projection L and K must be equal. So, the residue must be orthogonal to the Krylov subspace itself. We developed full orthogonal method and then saw that if the matrix is tridiagonal, if the matrix is symmetric, then nice properties come out of this, which uses something like a the Heisenberg matrix, which came while forming the while writing down the Arnoldi algorithm. This Heisenberg matrix becomes tridiagonal because it has a row below the main diagonal. So, it is a symmetric matrix with a row below the main diagonal and everything 0 after that. That shows that there will be only one super diagonal and everything 0 after that. So, it becomes a tridiagonal matrix, and any tridiagonal matrix gives us an advantage of using TDMA type of recursive algorithm, and we use that, we got conjugate gradient method, which is a very first method, we have demonstrated it later. Now, another method we thought which will be similar to the minimum residual method. Minimum residual is not an orthogonal projection method, K and L are not same. Here L is equal to AK, the oblique projection method we have chosen, which gives us general minimum residual method, and we did certain manipulation over general minimum residual method to make the steps more computation implementable. And then we have seen that GMRES can be applied for any matrix, however, conjugate gradient can only be applied for symmetric matrices. One thing very important to note is that what are the convergence properties of each method. If I go back to basic iterative methods, the convergent property depend on the spectral radius of G, which is iteration matrix, and this is important. I have asked several times questions in the assignment, and you can expect similar questions will come in the end sem. So, what determines the convergence property of different schemes? You can probably make a table while preparing. Basic iterative methods convergence property is dependent on iterative matrix. Conjugate steepest descent method convergence property is dependent on spectral condition number. Conjugate gradient method, convergence property is dependent on square root of condition number. GMRES conjugate convergence rate of is dependent on condition number. So, square root of condition number is much smaller number. So, convergence is much better in conjugate gradient, that we have observed. So, we thought that if similar convergence can be obtained for any matrix, but conjugate gradient is restricted for symmetric positive definite matrices. So, we looked into Langsos bi-orthogonalization, which solves an equation X is equal to B and a auxiliary equation which is not explicitly solved, but in background it is solved, is A transpose X is equal to B transpose, and found out the Krylov subspace for both the equation X is equal to B, that means AR, RAR, A square R, R0 AR, A square R0 etc., and A transpose X is equal to B star, which is R0 star A R0 star A square R, A transpose R0 star, A transpose square R0 star etc. These two Krylov subspace. Interestingly, if it is a symmetric matrix, then A and A transpose is same and both the Krylov subspace methods are same, and essentially biconjugate gradient will be transformed to a conjugate gradient method. However, for a non-symmetric matrix, we assume that the Krylov subspace related to A transpose is now my L space, and designed an algorithm for that. It is a very fast algorithm, was almost as fast as conjugate gradient, but as we are dealing with A transpose, and remember this again I have asserted while discussing, A transpose is from a computer science aspect, storing A transpose and doing operations with A transpose is difficult. So, that posed lot of computational challenges, and we have also seen, because there are a lot of matrix multiplications involved in the biconjugate gradient method, this is an unstable method. So, we thought that finding out the Krylov subspace and doing this A transpose thing, can it be avoided. So, we considered the case conjugate gradient square or biconjugate gradient stabilized method, where the auxiliary vector, residual vector etc. are thought of a polynomial form, and polynomials are very similar with the vector spaces. Polynomial can also be represented as a vector space. They can be decomposed into several orthogonal components etc. So, I assumed a polynomial space and found out a recursive relationship between the auxiliary vector and the residual vector, and devised biconjugate gradient stabilized, which is now a stable method, a better method than biconjugate gradient method, and has convergence property very similar as conjugate gradient method or biconjugate gradient method. Then we we've shown you some numerical example of the convergences etc. Then we thought that okay, in any case the convergence is restricted by the condition number, spectral condition number, spectral radius etc. of the matrix or the main matrix or the iteration matrix. Can we improve that? And we got the idea of preconditioner that multiplies something with the main matrix. So, if you are, instead of solving X is equal to B, you solve PAX is equal to PB, and PA has a better precondition number. And importantly, while doing this, I have shown for conjugate gradient and GMRES that the Krylov subspace actually changes to a different Krylov subspace, but it helps the solution to converge faster. And then we discuss what is left right preconditioning, why symmetric preconditioning can be advantageous for conjugate gradient type of method for symmetric matrices etc. And in preconditioning, we have also discussed that preconditioner can be approximate inverse decomposition of the A matrix, that is the best preconditioner. If I can have a preconditioner A inverse, my equation becomes identity X is equal to A inverse B, which is solved in a single state. So, the preconditioner P or M inverse can be very close to the LU decomposition of M A inverse, or M can be very close to LU decomposition of A, and we have used this exact LU decomposition. We will again take n cube operation. So, we will not do n cube operation, we will do few operations and go it very close to that, and we used something like symmetric Gauss cycle, symmetric successive over relaxation etc. for this preconditioner. And then we looked into another thing, that from a physical system being solved using matrix equation, how can it be made faster, and we got the concept of multi-grid method, where you observe that if I refine the mesh, the solutions converge slow. So, I will initially coarsen the mesh and the solutions will converge first, and but those solutions will not be accurate solution. So, then that I will use the actual mesh or refined mesh, which is a multi-grid method, and there are several cycles, several methods like relaxation is a solution method, and going from coarser to finer to coarser mesh, etc., which we have discussed. And these methods are what which can be used on top of the actual matrix solver to get faster solution. We have also discussed about block matrix algorithm that and parallelization, that how can we distribute the job among different processors and can get faster solution. So, this is as a nutshell what we have discussed about the in the syllabus. Is there any question? No. Okay, Sunil Kumar's question. Yeah, so some of the assignments I think I answered first, that some of the assignments some answers were not right, but we have updated it. Is it updated, right? The teaching assistants have already updated it, but these are not posted. Do not worry about it. All the concerns are addressed. Try to get it posted today, and the marks will be accordingly recalculated. Do not worry about that. There will not be any descriptive question. Yes, I should also discuss this. The questions will be very similar as the assignment questions. Most of the questions, few questions are actually much easier than assignment questions. If you just recall what is discussed in the slides, you can probably find it out. These are small applications of what is discussed in the slides. You do not need to do large calculations, and the questions are objective type. They are either multiple choice questions where more than one answers can be correct. In assignment, most of the cases one answer is correct, but here more than one answers may be correct. But these are like you can very simply identify whether more than one answer will be correct or not. And there are true false type of questions. So, these are the two types of question, multiple choice questions and true false type of questions. You do not need to do large calculations. When the questions I set and I tried to solve it, I did not use calculator. So, you can get it done even without a calculator, but the calculator will scientific calculator will be available on the terminal in which you will write your exam. So, you do not worry. The questions are objective type, no descriptive type things are asked. Some cases some of the definitions are something very close to the definitions may be asked, like is this a Krylov subspace, or is this the grade of the Krylov subspace, some question like that can be asked, or do you think that this is a relaxation step, a step will be in a multigrade will be told, and you have to identify that, some questions like that. Okay. So, yeah. So, I think we are kind of at the end of this session. What is the time here? They are not showing the time. Okay. So, yeah, if you have any further question, I can wait a minute or two. I am telling you regarding the exam, fundamental questions are asked, but these are very simple fundamental questions. If you have meticulously gone through the slides and the lectures, what I believe most of you have done, what I figured out from your questions in the forums and in the live sessions and your submission of assignments, if you have done the assignments sincerely, you should be able to answer all the questions. There is no much very tricky question, most of the questions are kind of straightforward. Aside, you focus on which case which solver will be applicable, what is the computational cost of the solver, what is the most computation extensive step in a solution matrix solver, this type of ideas, what are the convergence criteria for different cases. Why do we apply multi-grid? Maybe a few reasons can be given and you have to find out a reason, or whether we will be able to apply parallelization for this particular type of algorithm. You have to figure out which will be very simple, and most of the things I have discussed earlier. And from the previous discussions, a question like that, like you given a particular solution, given the null space vectors, how will you find out the other infinite solutions, or what is the dimension of this particular vector space, what are the do they form a basis, do they form an orthonormal basis, what will be the, is this the product you get out of a Gram-Schmidt orthogonal relation. Gram-Schmidt orthogonal relation will get you orthonormal vectors. So, you have to check that and have to answer this. So, these are basic, but again there are a lot of very simple questions like why do we use Gram-Schmidt, why we do not use Gram-Schmidt, but use modified Gram-Schmidt, which one is the cause, few causes are given and you have to find out that numerical stability is the issue, or for which matrix TDMA can be utilized, a few matrices are given and you have to find out. Other questions are like this. If you have covered the syllabus meticulously and gone through the slides sincerely, you should be able to answer this. Okay, is there any further question? Okay, thank you all. I hope you are helped by this discussion as well as by the course, and I wish you all best of luck for the exam. I want all of you to get very good grades. Thank you. Bye bye.